system. So I'm Lydie Staron. This is my colleague Pierre-Yves who's here, and my other colleague Stephane who's not. And I apologize for the hoarse voice. I hope I won't cough in the microphone too much. Right, so a short introduction about the challenges of continuum modeling of granular matter. I trust you're well aware of all these. So the main point is to manage to capture both static and fluid behavior for these systems, and tracking the boundary between the two, both in time and space, which can be crucial for some systems, specifically those with rapid transition between the two. So therefore, we probably need a precise description of a rheology. So that's has been the subject of a lot of work, as you all know. Probably that means understanding really precisely the micromechanical effects if we want to have a general picture of the rheology, and to be able to capture the transition from static to fluid and the other way around, the jamming transition or enjamming transition. And then supposing that we've managed that, we still need a mathematical solver to use our knowledge to model efficiently whatever systems we're interested in. So in that case, we'll be interested in a fluid picture of the granular matter. So you could use a solid point of view, but we use a fluid one. In that case, certainly what we need is a description of the effective viscosity. So the ideal would be to have an explicit description. So probably the most famous one, I mean the most well-known, is Bagnard ones, which relate the velocity to the shear rate. But it says little on the transition to solid behavior, that is a divergence of the viscosity that would, for instance, depend on the volume fraction. And so that's a difficult problem. A way to bypass this difficulty is to forego the explicit definition and use the effective frictional property to estimate the viscous response. So if you trust that everywhere in your system you can write the proportionality between shear stress and pressure using the coefficient of friction, and then if you also trust that shear stress and shear rate, shear deformation are collinear enough, then you can rewrite this like that, and then you've got a term appearing which has the dimension of the viscosity, and which may give a good picture of what the viscous response is. So as you see, it will be able to diverge without the need of a precise description of the divergence, which is quite convenient. And then if you want to have a precise description of that term, you will need a precise description of the friction, which is somewhat easier because it's a finite quantity, where viscosity is not finite. I mean, it diverges. So in the following, for mu, for the friction, we will use mu of I dependence, which has been talked of earlier. So the point of this dependence is that it relates the friction to the non-dimensional number, inertial number I, itself depending on the pressure and on the shear rate, in a way which tells you that the friction evolved from a static value to a dynamical value, which is higher, and so the effect of a large inertial number is to increase the friction, and so accordingly we'll also increase the viscosity. So if you trust that this can be used as an expression for the viscosity, which has been done before, we're not the first one to do that, then if your inertial number is small enough, we can have a linear approximation of that, and so you replace it in here, then you see that the effect of the inertial number will be to add a constant term to the viscosity that would otherwise vanish for very large shear. So it will be, as will be discussed later, it will be useful. So we're happy we've got a model. Now we need a solver. So we've used a volume of fluid method that solves the Navier-Stokes equation for a mixture of two fluids in 2D. So since it's a mixture of two fluids, it means everywhere in your domain, the viscosity will be the results of the viscosity of one fluid and the other. And so even if each fluid may have constant viscosity on your domain, the viscosity of the mix can vary a lot, specifically across the interface between the two. And that's essentially what volume of fluid methods are used to solve interface problem. And for that reason, they're well equipped with to cope with very sharp changes in time and space of viscosity, which is what will happen in granular matter. And another good thing is because we are also solving the concentration of each fluid everywhere, the interface between, say, your granular system and whatever fluid you have around, which is air, actually. It can't be whatever fluid. So and air takes care of itself. So in our case, we will suppose a granular matter with a viscosity that will be given by what I've just said before, the mu of I. And this is it. And we suppose the existence of air, which is just a fluid of constant small viscosity and low density. And so with that solver, we've decided, to see if it works, actually, we've decided to simulate the silo. So why the silo? So first, because it's a complex system, even though it's geometrically simple, it's just a flat bottom container with a hole. But you have coexistence of static zones, slow shear and rapid flow. So it's a real 2D dynamics because grains goes like this and like this. And it shows actually a non-trivial phenomenology with the Beverly scaling, which we'll discuss a bit later. But you have a constant discharge rate, which a normal fluid would not have. So this is our system. So here you just see the granular media. Imagine at the top of it you've got a layer of air, which I haven't shown, and at the top of my layer of air and at the outlet I put a zero pressure, so the thing flows down. And to compare with granular systems, we've run a discrete simulation using contact dynamics. So here what you see is the velocity field. The boundary condition at the walls is no slip, but it actually doesn't affect the result. If I put a free slip, I see nearly exactly the same thing. So we're left with one problem, which is what do we take for the parameters here? So for the contact dynamics, you just take randomly these values which coincide with a dense flow. So that's the contact friction and the restitution between the grain. And here we will just take this value and now consider that it's just a choice like that. In fact, it's not, but let's say it's just like that. So at first, we don't expect quantitative agreement, but we can still check if qualitatively this and this behave the same. So the first thing to look at are the inner deformation. So this is a granular system. This is a continuum 1 with traces just to see. So it gave me the opportunity to show how it behaves. Oh. So it doesn't behave like that. It does behave like that, right? Okay. So you've seen that before, I'm sure. A lot of people have worked on silo. Okay, we're happy with that. And now this is the continuum. Sorry. It is the continuum 1. Okay, so you see in black, this is the boundary between air and granular flow, and this is the granular. So it does things that the grains don't, right? Altogether, the picture is not too bad. All right, so then it empties itself, and then it does sustain shear stress, right? Not the whole thing flows out. Okay, so this is a film. It doesn't, it's a bit hard to compare. So here's our snapshot. So altogether it looks rather similar. It's rather nice, There are differences, though, essentially at the free surface. So you see that for the continuum model, there is a dip appearing immediately while the granular surface stays flat. But then it behaves better and better in the course of time. And we don't have the last picture. And in the last picture, you would see that the granular system is much more efficient at emptying itself than the continuum one is. But with this, it's not too bad, though. Now, the Bevel scaling, so that's what I was saying. Granular silo don't behave so simply. So they display a constant discharge rate with time, which obey a scaling where the outlet size only appears, and you don't have the height, neither the width of the system. So it essentially tells you that this area is probably screened from hydrostatic pressure, right? You wouldn't have that if it was Newtonian fluid, obviously. So here you've got the function of time, the volume left in a silo for both continuum and discrete. So for the discrete, so you see that you've got perfect line, so the discharge rate is indeed constant, and that's true for both discrete and continuum. And in both cases, if we vary the outlet size, we recover the Bevel scaling. So that's well known for discrete element methods. It wasn't clear for continuum simulation, right? So here you can see that granular systems are emptying themselves to a larger degree than the continuum one. That's one of the differences. So there is no quantitative agreement, so the prefactors of the Bevel scaling are different. You see also that the correction of the outlet size due to grain rigidity is not the same, obviously, because you're in continuum. Right. So something else to look at easily is the velocity field. So here are just maps to give an idea. So the velocity at the outlet are different for each system. They're geometrically the same. So the scale of colors have been normalized by the maximum velocity here. And essentially, it looks rather similar. So here you've got a section along which you can compare profiles to have a better idea of whether it's actually the same or not. So again, because we don't have quantitative agreement at this point, all quantity that is vertical and horizontal velocity are normalized by their maximum value, and then you plot, so here the horizontal and vertical velocity for different outlet size, and what you see, so for continuum and discrete, and what you see is the areas of rapid flows are actually well captured by the continuum model, and the areas of slow shear are not really well reproduced. So that's something that's known somehow, that local models are not so good at capturing slow shear areas. But okay, it's still not too bad. This is the pressure field. So in the discrete system, the pressure is average of a little volume. So it's still pixelized, but anyway, it's only one run. I did an average of different quantities run. And so you see that the agreement is not too bad. What's not too bad actually is that we see we've got high pressure areas and low pressure areas above the outlet. So a better picture is given if we compare what the pressure is like along profile. So just qualitatively, we see the shape between continuum and discrete is all right. How many minutes? How long did I talk already? 15. Okay, so I go. All right. So why did we take these values in the first place? Because so far we have only qualitatively looked at the system. But what if we want quantitative agreement? So these values we've taken because actually we've managed quantitative agreement comparing discrete and continuum in the case of the column collapse. And so just to show you, so I show you only one of them because there's not much time. So there's an orange column of granular discrete numerical thing, and a green outline, which is the continuum model. And that's the column collapse that we've seen several times today. And so you see that the continuum model is actually doing not too bad. So at the end, there is a problem, and that's, in that case, due to boundary condition. But altogether, quantitative agreement between discrete and continuum was achieved for these values. Oh, so it's a bit annoying, then, that for one system, a set of parameters allows quantitative agreement and not for another one, since here we didn't have. So I obviously have no time really to discuss the influence of rheological parameters. The only thing I can say is there is a set that we can find which allows the two prefactors to be the same, but for values of friction which are very huge, it's not really satisfactory. So the conclusion is that the visco-plastic law, the mu of I visco-plastic law, still does good results, in my opinion. I don't know what's yours, when compared with discrete simulation. And qualitatively, the agreement is rather encouraging. The I dependence is actually necessary, so I had no time to show that. But if you suppress the I dependence, the results are not really as good. The shape of the system that is a boundary condition are crucial, and the fact that we don't manage for one shape or another with the same set of parameters to achieve the same quantitative agreement mean that some physics is missing, and that's probably the non-local effects actually that were discussed a bit earlier. And all the more that recent work by other authors, including these, have led to good results in systems that were well, difficult. So I'll stop here. Thank you.
You think that the difference might be that dilatancy effects are important in the hopper?
No, I don't think so. I think it's more than that. So it's true that at the outlet the density is less, but I think it's more than that.
Far corner.
Could you just tell me what are the minimum and the maximum values of C, which is
The concentration?
yes.
Oh, 1 and 0. So actually, the concentrate. So if you look at where is that? Here. Okay. Well, I don't have the full picture. Here you will have C varying between 0 and 1 in 3 grid points. Here it's absolutely 1, and here it's absolutely 0. So actually, the two fluids are perfectly separated. And we start from a separated system, obviously. So.
Why do you truncate the viscosity?
Why? Well, numerically, I need to put an upper boundary, otherwise my computer doesn't know how to. So if I don't do that, it will really diverge mathematically. Numerically, I want to, because my shear rate can really go to 0. And I need that.
Could you imagine to have a setup where you could go continuously from the situation where your comparison works and towards a geometry, I don't know, you could just change your aspect ratio towards geometry where the comparison between discrete and continuum doesn't work?
All right, so it says it doesn't work where you have a slow shear for a long time over a large area. So for instance, the column collapse. So the column collapse goes wrong here because of, goes wrong, it actually goes right, but we don't capture the end, probably because of boundary condition. But if you look at the collapse, it's highly dynamic, and then it's static, and the shear between the dynamic and static zone is not really important to the system, which is dominated by large velocity. In that case, it works. If I do a quick cell something, it won't, because then the slow shear becomes very important. That is slow shear that we don't manage to capture. That's where the non-local effect seems to to dominate, as far as I understand them. I mean, we haven't.
You're calculating the viscosity from the pressure.
Yeah.
The pressure itself is being calculated from the divergence of velocity.
Yeah. So
I mean,
actually, it's not entirely implicit. So the viscosity we calculated is used by the pressure that step before. We're using the Navier-Stokes solver. It wasn't. So if it's Navier-Stokes, even you suppose your viscosity is not changing. So we don't suppose it is changing within a time step. All right. So the viscosity is actually calculated from the pressure the step before.
okay,
And so
but
you don't need to rewrite your solver in that case. You understand? So it's not looping the way you say.
So you're doing it from the previous time step. You're calculating the.
Well, then I've got my viscosity, and then I just the solver. I solve
But it's.
the equation.
But you're still using the pressure locally.
Yes. Yes. I'm using the pressure locally, just not for the viscosity.
Nor the strain rate either.
Yes, the shear rate is used at that moment.
And why do you enforce incompressibility? Because if there's more particles in a volume, the density is going to change.
No, I don't see why there should be a compressibility problem. We're solving mass.
Yeah, but you can imagine locally there's more air and less particles, and the density changes.
More air and less particles. The air is off. I mean, I've cutted it from the films. The air stays at the top. It's got a lower density. We start with the granular matter with the air at the top. And then you've got the boundary that can do weird things as it did in the film that you've seen. You know, it did a bubble. So only at the boundary you can have weird
So
things happening.
You don't permit local changes in volume fraction.
You don't?
Permit local changes in volume fraction.
Volume fraction is calculated as the average of, the density locally is calculated from the density of the two fluids and their local concentration. So where the concentration of one species is 1, you can't have any such problem as you seem to think about, if I understand what.
Perhaps
what
if this is a further question, it would be good discussed over drinks and
Yes,
posters.
I'm sure.